So we've seen partial derivatives. We're now going to build up the procedure to use those partial derivatives to find an optimum in 3 dimensions. So again, just to get ourselves into this 3-dimensional thinking, let's imagine that we've got some 3-dimensional space here under the camera, and we'll say x is this direction. So as we move to the right, we're thinking about a higher value of x. Whoops, put that there. And as we move down, we're getting a different value of y. Right? It doesn't matter higher, lower, it's just different. So if we've got some function z, which is some function of x and y, what that means is we're taking any given combination, right? So this particular value of x and this particular value of y, right? So we find these 2 lines, we find the point where they intersect, and we say for that particular point, here is the value of z. It is, this high off the paper. And we take another one, we get a different value, right? So we've got a 3-dimensional plane. We might imagine that with a piece of fabric or lens cleaner or whatever, right? So we've got whatever the particular shape of this surface is, that is our 3-dimensional function that we're dealing with. What partial derivatives are doing is they're saying, all right, let's take this underlying function and let's just look along a particular value of x. We're going to hold x constant, and we're going to ask what's happening with y. Right? So we're going to get some function, and that function might be a function of x, but what it's going to tell you is what's the slope with respect to y depending on where we are on the function. So here I'm kind of representing a Ripley function, but it might be that, say, at these low values of y, I'll think of this as low values of y around here, maybe we have a big positive slope. Maybe values over here, we have a slope close to 0. And maybe down here, our slope becomes negative in the x direction. All right, so that is partial derivatives. It's a little extra thing to wrap your head around, but mechanically, it's really straightforward. We just treat one of the variables as though it was a constant. So what can we do with this, and how do we build this up to our optimization? So again, we've got some function z, which is a function of x and y, and we calculate all these partial derivatives. So let's just start with our panicked intuition. Let's just take all the derivatives we can. So what are we going to get here? We're going to get partial f, partial x, which is just this treating y as a constant, taking the derivative with respect to x. We're going to get partial f, partial y. Here we're going to get the derivative of this with respect to x. So this is partial zx, partial x, and this is partial zy, partial y. Right, so all we're doing here, I'm really just putting down symbols on a page, but we're going to be applying the rules that we've seen to whatever function we get. And then we can also check our cross partial derivatives, which is our partial zx as we change y, and it's going to turn out that that is equal to partial zy as we change x, treating in this case, treating y as a constant. So how do we throw this all together? Let's try and keep our intuition as we do this. So the first thing that we're going to want to do is we're going to want to take these guys and we're going to set them both equal to 0, and then we're going to solve for x and y. All right. So this is analogous to when we look for where is f prime equal to 0 and we solve for x. It's just now we're solving in 2 dimensions instead of just solving 1 dimension of this problem. So whatever these functions are, we set them equal to 0, we do some algebra, we get an answer. The next part is we check these second derivatives to see whether or not we've got a local max or a local min, or potentially a saddle point, or we will also see there's a possibility of an inflection point. But all we're going to do here is we're going to say if zxx and zyy, if they're the same sign, that's going to mean that x is doing something like this, y is also doing something like this, so that point at the bottom is going to be a minimum. So that is if these are greater than 0, our critical point looks like a local minimum. If they are less than 0, then it looks like we're looking at a local maximum. And if the sign is different, so zxx, what would that be? I guess zxx, zyy, if one is, well, zxx, let's just say this is greater than 0 and zyy is less than 0, or vice versa. In that case, we're looking at a saddle point. So with a saddle point, you've got this direction in one dimension, this direction in the other dimension. You lock those together, you've got something that is saddle-shaped, which is, do this with your hands. Hopefully that makes it clear. And then we're going to have to check to make sure there's nothing funny going on in the corners, right? So maybe we have something like this saddle point. We can see that although we're flat in the x dimension, flat in the y dimension, when we go off here, we're going uphill. When we're going off here, we're going downhill, or whatever the case is. We're going different places, right? So maybe we have something that looks like this, where it looks like a maximum, but maybe it curls up in the corners. So we're going to check the cross partial derivatives. Right, so let's just say that this is something with a local maximum. In the x and y dimensions, it's fine, but if this corner pulls up for whatever reason, then although we find this flat point here, it's not a local max because we can go off over here and find a better max. So let's put this all together and lay it out. And for that matter, let's go ahead and come up with a function. So let's just say our function is, let's see, let's do x squared plus y squared plus xy. Nothing crazy. So what do our derivatives look like? Well, zx is going to be 2x plus y. Zy is going to be, bring the exponent down, 2 times y to the power of 1, plus the derivative of this term with respect to y, treating this like a constant, which leaves us with x. Let's go ahead and solve these now. So these are going to be equal to 0. Let's just throw them together. What are we going to get here? Well, we're going to pretty easily find that x equals y, right? We can see the symmetry there. Right, so 2x plus y equals 2y plus x. We rearrange, what are we going to get? We're going to get x equals y. All right, so if we substitute that in, 2 times x plus x is 3x equals 0. All right, so x and y are both going to be equal to 0, right? So they're going to be both happening, let's say, right in the middle of our grid. That's fine, right? So we found our critical point is 0, 0. 0x, 0y. Now, let's find zxx. What's that going to be? Well, that's just going to be 2. Zyy is also going to be 2. All right, that's fine. And then zxy, what's that going to be? Well, the derivative of this with respect to y is 1. And hey, that's also the same as zyx. Now, I should mention that we're always going to see the cross partials are the same. We aren't always going to, well, we are going to see that zx equals 0, zy equals 0. But we aren't always going to see this sort of symmetry, right? This is just because I was lazy and made a kind of a boring looking function just so I didn't have too many moving parts. So zxy, zyx are equal in principle. Zxx equals 2. It doesn't have to be the case that zyy is the same, but it just is because I'm lazy. All right, so what have we got? Well, we've got zxx and zyy are both greater than 0. So whatever's going on here, we're looking at a minimum. Right, so at this intersection, if let's sort of imagine we're looking at this from this angle. In the y dimension, it looks kind of like this. In the x dimension, it looks kind of like this, right? So we can kind of imagine this bowl shape around this. Kind of, sort of. I'm being a little bit sloppy here, right? So we certainly have that. We're going to have something kind of weird in the diagonals, though, right? So if we have positive x, positive y, we're going to have basically this bowl shape, right? So this is just going to be sort of a nice circular bowl. And then here we're saying off in this direction, we're pulling this up. We're adding on some extra things. So z is going to be extra big in this dimension, right? So z, let's just say, gets extra over here. And then likewise, negative times a negative, z is going to be extra big in this diagonal. Over here, z is going to be extra small, right? So we have some big value of x times some big negative value of y. So rather than just bowl shape, we're stretching it down over here, likewise over here. All right, so let's check our last condition. Our last condition is that our cross partial, the product rather of our cross partial, has to be smaller than the product of our second partials. So zxx times zyy, which, as you know, is 2 times 2. This has to be bigger than zxy squared, right? Which I kind of think of as zxy times zyx, right? So we've got a product times, compared to another product, which in this case is 1 times 1. So here, very nicely, because we've met this condition, we can say that this critical point is in fact a minimum, right? We can certify it. Now, what I would recommend doing is start tweaking this simple function, try some different things out to try and push this in other directions. So let's do a really quick modification right now. Let's see if we can make this value bigger without changing this figure. All right, so zxx is this 2x term. So if we have a big coefficient here, maybe things will be bigger. Let's throw in, let's say, 10. So x squared plus y squared plus 10xy, well, our derivatives are now going to be 10y and 10x. Putting it to the right because that's where I've got a little bit of space. So now this is going to be 10. So now this is going to be 100, which is going to be less than 4. Let's quickly verify. So we've got x squared becomes 2x. Take that derivative again, we've got 2. This, there's no x, so that doesn't affect this. So in this case, what have we got? We've got our corners matter more, which means although it's shaped like a bowl in this dimension, these off corners are going to be pulling it down to something lower than what we've got here. Right? So that shape is going to change. So before we had a bowl with some slight distortions, right, in these corners, kind of falling down this way, kind of almost a little bit shaped like this. But now with this bigger coefficient, we're getting this extreme result where we fall off this cliff. So try other things. Try breaking other conditions. Try adding a negative coefficient here and thinking about how this all changes, and try plugging it into Wolfram Alpha so you can see how it actually plays out. Now, if you're still watching, let me tell you a little story. This is a freebie. This is not going to be on the exam. But here's a fun little expected value story. So I got this $1 coin at the Golden Nugget in Laughlin, Nevada. This is Fremont Street in Las Vegas. So I was there for an economics conference as an undergrad. So I decided to go to grad school. So I was going to this conference to meet who would become my dissertation advisor, basically to try and get myself into that program. And I was walking through the Golden Nugget with my buddy Wah, and I said, "Hey Wah, check this out. I'm going to put $1 into the slot machine, and you know what's going to happen? I'm going to lose that $1." I was doing some expected value math and basically making the point of slot machines are stupid. So I put in my $1 and I won back $5. I've kept one of those dollars because, you know, even though I can't buy myself a Coke with this, it's kind of worth more as this little souvenir for me. In any case, as usual, if you've got questions, go ahead and ask in the usual places.